Recording in progress.
So welcome once more. Let's begin with the lecture. I'd like to give you again a little overview on the table of contents. We've done the intro. We've introduced partition functions. We then derived various state functions and thermodynamics. And the last couple of weeks, we've been busy going through the various ways how energy can be distributed over the degrees of freedom in your system. So we factored out the partition function in these various energetic modes. And then we considered specific examples of partition functions, which we more or less derived in class, okay? So we obtained the translational, the rotational, the vibrational, and the electronic partition function. Today, I'd like to move ahead and enter the chapter, which is the cherry on the icing, okay? It's really a beautiful chapter. It's the equilibrium constant. So you learn this in high school, right? That K is the ratio of some concentrations, right? For instance, products and reactants. And then when you enter university, you also learn that delta G equals RT ln K. But so far, nobody told you why or how, okay? Now, this really tells you that in terms of implications and importance to chemistry, this quantity can hardly be overstated in its importance, right? So you can literally, with these simple relationships and knowing about the energy in your system, which determines everything, you can predict the future of chemical processes. You can predict if it's rather product A or product B that will be formed, okay? So this is the magic of chemistry. We can transform matter, and now you're able to not only do that, but also predict and control that, right? Now, there are many ways to define understanding. One of them is that you understand something when you can predict it, right? So according to that definition, unless you can predict which compound will form over the other, you have not understood chemistry, okay? I not necessarily prescribe to that definition, but it's a nice one. So let's enter this by doing a little recap on what we know so far. So we'll enter the chapter 5.1, which we call an intro. And let's just note down some things we have derived already, but just to refresh our minds. So our internal energy U, the expectation value of our energy, the microscopic energy, right, is minus derivative with respect to beta of logarithm q. And if you prefer, derivative of logarithm q with respect to temperature at constant volume. So this notation, right? U is always a constant volume, right? What's the fancy word for constant volume? Anybody? Yes, I heard it somewhere. You? I don't know. Isochoric. That's right. Now, that means pressure varies like crazy, and we get it from kBT derivative with respect to volume of logarithm q constant temperature. Right? Now, this is often a confusion. How, if something like volume is constant, how can I measure a pressure or some derivative and with respect to the constant variable? But that's very easy to intuitively understand. Imagine you're standing on a slope, skiing or something, and the slope is non-zero, but you're standing, right? That's where you are, but there's a force acting on you. Right? The derivative is non-zero, but you can resist or something holds you back, right? That's okay. The gradient is still there. Right? The heat capacity, CV, two kBT dt logarithm q, constant volume, plus k t squared dt second order derivative logarithm of q constant volume. And then for the entropy, we had multiple expressions, right? And these expressions can all be converted into each other. They're all true, right? So you get to pick whatever is most convenient for you. But we noted kb logarithm q plus kt dt logarithm q constant v kb t dt logarithm t logarithm q v. That's the same as u over t plus kb logarithm q equals minus kb beta d beta logarithm q plus kb logarithm q. And we'll be using this expression later on. So we started out by this refresher. And I'd like to go now, and that is directly related to this delta G after the free energy, okay? So our first job is to get towards the free energy. And what we have is our cherished first law, and the second law, which we derive, but it still holds. Okay. So how do we get to this free energy that determines everything, right? So that's our first job. So this is free in the sense of being available, right? So the system, this is the energy that the system is willing to release in a spontaneous process, or the energy the system requires if we wish to turn non-spontaneous process to make it happen, right? So free means available. So there's if you don't believe me, right? I can quote and argue from authority. Boltzmann made this statement: free energy is the pivot point in fight over existence and evolution in this world. How about that statement? Okay. So if I fail to motivate you, maybe Ludwig does. He also, by the way, made a nice comment on how to do science. Which, according to my miserable translation, reads something like, speak up on truth, write such that it's clear, and fight with it till you're done. So the truth-seeking mission is, of course, at the heart of academic science, and but then you also need to write about it, right? It doesn't help anything if you know about it, and then you cannot communicate it. And this is a struggle, right? So you have to keep on doing. The way I see it is you're never done. There's this thing, if you read really excellent papers in the literature, they usually stand out because they are written in a very clear way, right? So if you find such a paper, right, which is written in such a way, just keep it also ready for that reason. It's a good sign. There's this saying that a paper is finished once you can no longer remove anything from it, and you can no longer add anything without making it worse. Um, so now, two quotes by him, and now let's get going. So du is, and again, that's just the first law. And now we go isochoric. So our volume work is not happening. Now, ds is larger equals dq over t. And from that, of course, t ds larger equals dq. And so we can substitute this here. And we get du minus t ds smaller equals 0. Okay. So we put this inequality here for dq. Now, we factor out our differential, and we have u minus ts, which must be smaller equals 0. So this is the difference, right? The balance between your internal energy and temperature times entropy, right? And this balance, right, is what we call the free energy. So we define that to be u minus ts. And in any spontaneous process, right, this must always be smaller equals 0. Right? So this is our definition, and this is our Helmholtz free energy. Right? And remember, that's for the isochoric regime. Yeah. So the history of the world can then be plotted as a function of time, and your changes in A, sorry, not changes, the A, right? And then you see your A is changing, so the dA is smaller, right? So your A is going down, and at some point it levels off, and then nothing happens anymore, right? And so that's the dA equals 0 regime, and that's also known as equilibrium. Now, it's not entirely true that nothing is happening anymore, because define happening. You could, for instance, think about an oscillatory reaction. There are equilibrium states that involve movement, right? But these are they're very exotic, and as soon as you try to extract energy from it, it will collapse, right? But you do have such processes where actually something is happening formally, but it's still in equilibrium. But for most intents and purposes, the movement of atoms correlates with the spontaneous movements of atoms is related to a lowering of the free energy. And in this regime, your dA is smaller zero. That's the non-equilibrium. Okay. So you see from these couple of steps here, right? We going with the first law and second law, you arrive at this free energy, at this inequality, right? So it's a necessity. It's not arbitrarily drawn out of some academic straws. And so we can now operate with this balance and simply insert the expression for the entropy, which we had refreshed up here. Right. This is S. So let's insert it and see what happens. U over T, that's nice. That's going to cancel. Plus KB logarithm Q. In other words, your Helmholtz free energy is simply minus KB T logarithm Q. Okay. This equality is quite mind-boggling to the macroscopic chemists. Just to remind you, this free energy, which Gibbs and the old thermodynamics school inferred from observations of enthalpies, entropy, and so on, is being linked now to the partition function that sums over the states of Schrödinger's equation, right? And this is known as the Mathieu bridge. So it carries an extra name because it's so amazing. Now, recall, please, our total differential in A is minus S dt, right? So S being dA derived with respect to t, minus B dV, dA with respect to V, okay? Now, let's consider pressure. Minus dV dA dV. We can differentiate our dA now. Okay, so that's consistent with what we've also obtained for the energy already before. So all of that is the isochoric regime, and 18th or 17th century, nobody cared about that. We wanted isobaric conditions, right? So we want the enthalpy. Enthalpy equals U plus PV. We can insert these quantities and we find kBt squared dt logarithm Q for U. And P is coming from above, and we multiply it with V. Okay. So now you see the enthalpy in terms of Q. You haven't seen that yet, I bet. And now, once we have the enthalpy, of course, we want the Gibbs free energy. So your free energy plus PV. And again, we simply use Mathieu's bridge for the Helmholtz energy, and we add the same PV term. Yeah. Now, of course, we'd like to look at the same way we looked at the pressure, right? Once more. We differentiate G with respect to P. We simply recover the volume. And, so this is the PV derivatives. And so compare versus ET. dg dt, this turns out is the same as dA dt, which is minus s. Okay. So dg equals v dp minus s dt, and the A, as we already noted above, minus pdv minus s dt. Okay. So this is how we deal, right? And you have the ideal gas law: pressure, volume, temperature, right? Our three beloved variables. Now, there is another variable that people always like to neglect. Anybody knows which one? Correct. The particle number, right? Nobody likes to talk about this. I don't know why. It's really weird. And it's actually the most interesting one. So there's another force, right? This is your pressure is your volume force, right? The volume is the pressure force. Entropy is your temperature force. And then there's another force. There is a fourth force, right? And that's the one so if you think about nRT equals PV, right? We have all the four. This is, of course, a constant, right? And that's the particle number. So you mentioned the fourth force. I change my free energy with respect to particle number. How do I call this property?
Change entropy.
So I change my free energy. Particle number. And before we change it with respect to temperature, then you get the entropy. Yes, you get mole, energy per mole. You know the, how we call that? The force, the particle force. Who knows what it's called? That's right. It's the chemical potential, right? So we are looking now at this derivative, some energy with respect to particle number, right? And this is what we call the chemical potential mu. Now, if you're a chemist, your heart should get soft now, right? Because we are changing particles, right? Now, you can, of course, take this view that I'm transforming this compound into another one, and my total number of particles is fixed, right? But that's a little bit of a naive view, right? What is really happening is that in your sample, you have Avogadro's number particles of some starting compound. And that starting reactant, right, is decreasing in number, while at the same time, the number of products goes up. Of course, you could go onto each one of them and look how they slowly transform. But that's not very elegant. It's much better you start counting. You're doing your statistics, right? And you then wait a time interval, and you redo your statistics, right? And so that statistics is exactly what this chemical potential is quantifying. Okay. So all chemists love the chemical potential. The physicists hate it. They don't know what it is. And so we have an advantage. Now, what does this mean? Right? All of thermodynamics probably you've studied. I don't know. Have you studied the chemical potential in your thermodynamics class? You did? Okay. So then let's go quickly through this. We extend our total differential. dA is not only our entropy and our pressure, but also our chemical potential term, right? Oh, sorry. And that was the isochoric case. If we go isobaric, I just have to smile because your tutor recently had an exam. He was a little bit swimming on the isochoric, isobaric distinction. So if ever you wish to pull his leg, could try that one. He did pass very well, though. Okay, so is the chemical potential rather like pressure and volume, or rather like entropy? From these couple of lines, you see it's rather like the entropy, very convenient for us. The ADN is the same as the GDN is mu. Okay. So how does your free energy, right, the thing that matters most, that determines your fight of existence, how does it depend on temperature, on volume, on pressure, and on particles? That's what you've seen now. And you now know how it connects to the microscopic partition function. Are there any questions? All good? Okay. I'd like to thank you for your attention, and I see you on Thursday.